Searching on one. And I saw. I
Okay, page 36. We'll go through this slowly, but I want to start introducing graphing polar equations. You can also have your graphing calculator out as well. We'll refer back to the calculator and just get comfortable with the calculator as well. All right, so page 36. Okay, so let me read through the notes here. A rectangular coordinate system is only one way to navigate Euclidean plane. Such coordinates x, y is known as the rectangular coordinates. They're useful for expressing functions of y in terms of x. Curves that are not functions are often more easily expressed using an alternate coordinate system called polar coordinates. In a polar coordinate system, we still have the traditional x and y axis. The intersection of these axes, the old origin, is now called the pole. Similar to navigating on the unit circle, we can now get to any point in 2D space by specifying an independent choice of an angle theta. So just identify some theta of an angle theta from the initial ray, from the polar axis, and then we walk out that terminal ray a specified amount r in either direction, either towards or away from that quadrant. Okay. Although the angle is the independent variable, we express the point in polar plane as r comma theta. So theta is independent, r is dependent, but instead of theta r, it's represented as r comma theta. The point to the right would have coordinates of 4 comma pi over 4. So my theta is pi over 4 because we're always measuring from our polar axis, and our angle measure is pi over 4. And then if we want to, once we identify what angle measure we're involving, then we're either walking away or towards that quadrant. So pi over 4 is in the first quadrant. This is positive 4. So we're going to walk out 4 units. 1, 2, 3, 4. That's where that point lives. Now, if it was negative 4 comma pi over 4, then we're still along this pi over 4 line, but starting at the pole, instead of walking towards the first quadrant, we're going to walk away from the first quadrant. So the opposite quadrant is going to be third quadrant, be 1, 2, 3, 4. So the negative and positive just tells us whether you're walking towards that quadrant or away from that quadrant. Okay, so this order pair here is 4 comma pi over 4. Again, this is my radius and my theta pi over 4. Negative 4 would be in the third quadrant. Yeah, if it was negative 4 comma pi over 4, we can do that. 1, 2, 3, 4. We can represent this location as negative 4 comma pi over 4.
What'd you say about 4 negative pi over 4? 4 comma negative pi.
Right. If it was 4 comma negative pi over 4, then we're going to walk out. We're going to first figure out where that measure is. So negative pi over 4 will be in the fourth quadrant. And then 4 negative pi over 4 will be walking here, 2, 3, 4. Let me identify that location there. Here. Exactly. Yeah. So every point on polar coordinate have infinite representations because we can always create infinite terminal angles to that same location and either walk towards or away.
Yeah.
So exactly, yeah, we have multiple ways of representing this. If we want to walk out in from the counterclockwise position, we can go all the way to this degree, this measure, which is 5 power 4, and then walk 4 units towards 5 power 4. And that would also take us to the same location over here.
Would -4 negative, comma -5 for being the second quadrant?
If it was -4, negative power 4, that's right. It'll be in the second quadrant over here. Yeah. Okay, let's try example 1 first, and then I have an example 2 that comes after. Okay, so example 1, it says find several other equivalent polar coordinates for the point shown above, then find the equivalent rectangular coordinate. Okay, we'll do that for part B. So let's do part A. Okay, find several equivalent polar coordinates for the 4 and power 4. So okay, so we're going to find different variation of this point. So this can be 4 comma power 4. Another option is we can go to 5 power 4 and then walk away from 5 power 4. So what would that look like? I want to represent this location from this perspective. Yeah. So the 5 power 4 will be in the third quadrant, but -4 will tell us to walk away from the third quadrant. So we have that angle established, which is we'll walk away from third quadrant. So -4 comma 5 power 4 is also equivalent. Now we can create different variations of my radian measure by either adding or subtracting 2 pi to this, and then that will create another pair. So for instance, if I subtracted 2 pi from pi over 4, what would that give me? Yeah. So -7 pi over 4 is the same thing as pi over 4. So this will also land me in the first quadrant, right? If I add and subtract 2 pi, I'm exactly in the same location. So 4 comma -7 pi over 4 would also be the same representation as the previous two. And I can take 5 pi over 4 and what if I subtracted 2 pi from 5 pi over 4? -3 pi over 4 will be the same thing as 5 pi over 4. It's just getting to that angle measure from a different direction, but it's still in the third quadrant. And if we walk away from the third quadrant, we'll still end up in the same location as 4 comma pi over 4. Any questions there? It says find the equivalent rectangular coordinates. So let me produce notes here. Now equivalent, let me draw a triangle here, show the relationship between polar and a rectangular coordinate. So if I want to find this point up here, normally we would go X and Y, right? I will go to the right X and up Y. That will take me to that point there. But we also have polar coordinate available now. Instead of going along left and right, we're just going to find the angle measure, figure out the angle measure of that hypotenuse, and then we can walk towards that hypotenuse. So it's using theta and r to get to that same point. So the relationship that's going to allow us to connect between one and the other is using trig. Okay. So let me ask you this: what is sine of theta equal to for this triangle? That again? Sorry, my bad. Not this problem here. Yeah, in terms of this, the formula here. So yeah,
Y.
right. Hypotenuse, sorry, opposite over hypotenuse. So if I want to solve for y here, what would that look like? Yeah. So this is my conversion from my polar to rectangular. If I have the r and theta, I can plug that r and r sine theta, and that will give me the y portion of that to get to that order pair. Okay, likewise, what's cosine of theta equal to?
X over R.
X. If I want to solve for x equals.
R.
So if my radius is 4 and my theta is pi over 4, let's solve for x and let's solve for y. So x equals what? So it'll be 4 cosine pi over 4, which does reduce to what you said. Y equals r sine theta Okay, let me do part B here. That I'm going to add to example 1. Let's say we want to convert order pair 2 root 2 to root 2 back to polar coordinate. We know that going backwards, we're going to get to 4 and pi over 4, but I want to show a formula that can help us get there. So if I'm setting at the x and y, and I want to get to r, guess what that relationship is? Pythagorean theorem, right? So my r is just going to be square root of x squared plus y squared. And if I'm sitting at x and y, and I'm trying to get to theta, which trig function will help me get to theta? Tangent, yeah. So we know the inverse tangent. So we know that tangent of theta is equal to y over x. So therefore, theta is inverse tangent of y over x. Okay, so let's see if we can convince ourselves that we can go backwards using this formula. So here's my x and there's my y. So this is 4 times 2 root 2 squared, which is 2. 4 times 2 is 8. 8 plus 8 is 16. Which is 4. That's back to where we started. And we know that tangent of theta is y over x. So tangent of theta is equal to 1. First quadrant. Pi over 4, so r comma theta.
Doesn't matter which angle I give. Like what if I gave like 5 pi over 4 like that?
Right. So we have restricted values when we do inverse for tangent is the 4th and 1st quadrant, sine is 4th and 1st quadrant, and then cosine is 1st and 2nd quadrant. So so we're never going to be in the 3rd quadrant. If it's positive, it's always 1st quadrant. Okay, why use polar coordinates? Graphs that aren't functions in rectangular form can still be functions in polar form. Some of these curves can be quite elaborate and are more easily expressed as polar rather than rectangular equations. All right, so we're going to graph, and then as we graph, we can also use our graphing calculator to confirm. Okay, and as I show you these properties, we don't have to necessarily memorize them, but I think it's good to kind of have a feel for all these properties, and then just use your calculator to help you, with anything that you're stuck on. But it's good to know how these graphs are created.
Could -4 also be a solution for R?
No, principal value, if there's not an equation, if root 16 is by itself, it's always going to be positive.
Okay.
If it was R squared equals 16, then R could be plus or minus. Okay, so let's start off by just showing the calculator, and then we can talk about the graph by hand. So you're going to put your graphing calculator in polar mode. So you're going to go to mode. And then you see a couple of lines down there, you got function, parametric, polar, sequence. You're going to go and select polar, POL. Make sure you're in radian mode. And now when you get y equals, it'll get you something in terms of r equals. It won't be y equals anymore. Okay. And we'll type in r equals cosine theta. And theta is going to be where the X button is. Go to zoom. And I think it just depends on how you want the graph to look. Sometimes zoom stat looks better. Sometimes zoom fit looks better. So you can try both those options and just see what they look like. Zoom fit, zoom. I did zoom stat there. Zoom fit. Oops. Yeah. Sometimes this may be a little bit too large. So I think usually zoom. I think we can always just draw a box around that as well if we want to zoom in on a very particular portion of the graph. If you go to second graph, you're going to see your theta value as we go across. Okay, I want to show this how we can do this by hand. Okay, but at least we know that we can also use our calculator to figure out some of these what the graph would look like. Okay, so even though R is first and theta is second in terms of order pairs, I'm going to write this as theta comma R. So we're going to create a bunch of order pairs, and we're just going to plug in and see what we get. Right. So my function is cosine of theta equals R. Let's start off with 0. Okay. So if I plug 0 in for cosine, what's cosine of 0? 1. My radius is 1. So let's plot that point. That means at the radian measure 0, I'm going to walk out 1 unit. Okay, let's do pi over 6. And some of these we just have to kind of estimate. Okay, but I want to, but once we get comfortable, then we kind of just pick out the values that are more spread out because we know what the shape will be. But just for now, I want to kind of walk through some of the values here. So pi over 6, what's cosine of pi over 6?
Root 3.
Okay, root 3 over 2, which is around 0.7. Okay. Okay, so the best of our ability here, well, let's see, this is 30 degrees. 30 degrees is pi over 6. We'll just walk out 0.7. So to the best of your ability, just guesstimate where that 0.7 is. Ultimately, you should be able to begin to see this circle kind of forming along the way. Okay, next up, let's try pi over 3. All right, what's cosine of pi over 3? So pi over 3 is here at that 60-degree line. Go halfway. Next up, let's try pi over 2. Yeah, so cosine of pi over 2 is 0. So that means along this vertical axis there is going to go back to the pole. So you kind of imagine half a circle has been created, right? So we're going to keep going until we get that circle created. Next up, let's try 2 pi over 3. Okay, cosine of 2 pi over 3 is... Now, 2 pi over 3 is over here, right? It's that 120-degree line. But that negative 1/2 tells us to go where? You have to go opposite, right? To go in the 4th quadrant. So we're going to go along this 2 pi over 3, but opposite side, we're going to go half distance out. Okay, next up, 5 pi over 6. Yeah, cosine of 5 pi over 6 is negative root 3 over 2. So 5 pi over 6 is over here, but we're going to walk away from 5 pi over 6, 0.7. So somewhere here. And then pi, cosine of pi is negative 1. So pi is over here. But rather than walking towards pi, we're going to walk away from pi. So we're going to end up where we started. So we can trace the polar graph that's created, and also we know the direction that it's headed, right? It's kind of going along this path there. So our graph is going to trace counterclockwise. I'm abbreviating that, CCW, counterclockwise. And it's going to complete one rotation on the interval from 0 to pi. Now the coefficient is also telling us something. What's the coefficient in front of this cosine here?
1.
1. Based off the circle, what is that 1 referring to? The what of the circle? Diameter. It's a diameter. So that coefficient is going to be the diameter of my circle. We can use that knowledge to help us take some shortcuts. We don't have to do all this if we kind of have an idea how things will go. So what do you think 3 cosine theta will look like? Yeah, it'll stretch out all the way to 3, right? It'll have a diameter of 3. But I think if we just do a couple of order pairs, we should be able to get enough information to sketch out our graph. So we'll start at 0. Cosine of 0 is 1. 1 times 3 is 3. And we know it's going to trace out in this direction here. If I do pi over 2, cosine of pi over 2 is 0. So we know that's going to take us halfway. And then at pi, cosine of pi is negative 3, or negative 1, sorry. Negative 1 times 3 is negative 3. It'll take us back to here. So if you just count 1.5 here and just count 1.5, you can kind of have an idea where these points will land, and you can kind of sketch out your graph that way. What if we were trying to graph r equals -3 cosine theta? Where do you think what do you think is going to
It'll be
happen?
on the left.
Yeah, it'll be reflected. Yeah. So -3 cosine theta will just be over here. Again, there's no need to memorize all this. It's just, if we know these properties, we can we kind of have an idea where the graph will be. You can always use your calculator to confirm everything that you're doing, but just want to show you some nice properties here. And then also notice your cosine circles will be symmetric about the what? Yeah, symmetric about the x-axis. So likewise, what do you think the sine will look like about the y? Yeah, so see if you can sketch r equals 4 sine theta and r equals -4 sine theta. You don't have to do a whole lot of order pairs. You kind of have an idea where it's going to be. You know the diameter. You know kind of where that circle is going to live. And then you can also sketch out r equals -4 sine theta, right? It'll be above each other, right? Over the y-axis, over the x-axis. All right, so what do you notice about the above graphs? A couple of things here. One, the diameter of the circle matches the coefficients. We're able to trace out a full rotation from 0 to pi. And then cosine graph is symmetrical about the x-axis, and sine graph or sine circles are symmetrical about the y-axis. Not only circles, I guess other polar graph shapes will always have that symmetry. Cosine is symmetric about the x and sine is about the y. Okay, everyone have these properties written down? Okay, let's look at example 3. Now, these are going to be shapes that kind of fall under these category called limacons or cardioids, and they kind of have, yeah, some of these will kind of have this inner loop about it or this heart-shaped graph about it. Let's start off with 2 plus 2 cosine theta. Okay, again, we're just going to find unit circle values to kind of help move us along the graph. Or if you want to start off with your calculator, you can. Just kind of give you an idea what the shape will be. So 2 plus 2 cosine theta. We do zoom 0. Okay, let's start with 0 here. So cosine of 0 is 1. 1 times 2 is 2. 2 plus 2 is 4.
So the diameter is the coefficient plus the constant.
Yep, yeah, I'll go over those details a little bit later, but we're going to sketch the graph out first. But you're right, yeah, it's going to involve adding and subtracting the coefficient and the constant. Okay, so we'll go down the line here and fill out these numbers. Also, the nice thing is that there's symmetry about this. So when we make our way halfway through the graph, we can just repeat that process and fill out the rest of the graph, copying what we did above. So here, looks like when we get to pi, it'll only reach half of the shape. It kind of has that heart shape about it, right? Cardioid shape. Once I have half of it, I'm just copying what I'm doing below to get the other half of the shape. So cardioid is going to complete its cycle from 0 to 2 pi. Right, like you guys mentioned, the diameter is formed by adding the constant and coefficient. And here, there's an inner diameter of 0. Sometimes when we're dealing with numbers where the constant and coefficient are not zeroing out, then the -1 or +1 or 2 is going to give us some additional insight as to how the graph is showing. But here, the inner diameter is 0, so there is no diameter, there's no inner portion here. It's zeroing out. Okay. We'll show you what the other, what it looks like when the inner diameter is -1 or the inner diameter is 2. But if the inner diameter is 0, you know it's going to have that heart shape, that cardioid shape about it. Okay, let's try this next one. 1 plus 2 cosine theta. You can start with your calculator if you want. Okay, so I'm just picking out some convenient points to use. I start off with 0. 0 will give me 3. Pi over 3 will give me 2. Pi over 2 will give me 1. And 2 pi over 3 will give me 0. So it's going to create a polar 0 at 2 pi over 3. But then at pi, it's going to give me a -1. That -1 is going to kind of force this graph to go within itself. It's going to create this inner loop. And that will take us to the halfway point for our graph. Let me highlight that. Then after -1, it's going to get to another polar 0, and that's going to close the loop. And once it closes the loop, then it's beginning the path back to this starting point. So here I'm only providing the order pairs up to the halfway point, because after that we can kind of just follow the same pattern above. So this is a cardioid with an inner loop called the levason. And here my outer diameter is just like we did before. We add the coefficient and the constant. 1 plus 2 is 3. But then the inner diameter, inner loop diameter is 1 minus 2. And if we get a negative number doing a constant minus the coefficient, then that tells us that we expecting an inner loop. So if the constant is less than the coefficient, we get that inner loop to show up. And as you are graphing it on paper, also see if you can get that picture to show up in your calculator. Now, if the coefficient is greater than if the constant is greater than the coefficient, then this part is not going to, it's going to kind of stick out a little bit. So we call it the typical levason. There are no polar zeros here. But we can still see some of that relationship here. Here, if I add the constant and the coefficient, 2 plus 1 is 3. So kind of think of that as the outer diameter. I guess in this case, it's more like outer or the larger radius. And 2 minus 1 is 1. So that's this distance.
We have to know the names or.
No. I just want you guys to be able to know how these graphs are created. So if you're looking at your calculator, that you're not completely lost, right? You don't like, it's nice to know how things are getting created. But yeah, you don't have to do any of the order pairs on the test or on the AP exam. But this is really, I think it's good knowledge to just have. Okay, so we got through half of the graph. It's good that we have 2 days devoted to this, since we didn't really cover this in pre-calc. So after we get through the graphing, then we can get into the area and the derivative and all that. Okay, so tonight your homework will be finishing up the 9.6 and the AP practice. So page 28 through 35. but skip number 6 on page 35. All right, come get your phones.